Okay, let's begin. We ended last class talking about the binomial theorem. And when it applies. Now, when it applies is just as important to know as what the theorem, what the actual formulas are. So let me write that down again. We looked at binomial theorem, binomial probabilities. Binomial theorem is something else. I'm tempted to talk about it now.
Do it.
Stop, Jhevon, stop. Okay, binomial probabilities.
Follow your dreams.
Like, well, actually, fun fact, the reason why it's called a binomial probability is because the binomial theorem is never mind. Okay. So, binomial probabilities. You are in this situation. If one, an experiment is being repeated. Right? So the same thing is happening over and over and over again. In fact, we say it's happening n times. Right? So that's the number of times the experiment is being repeated. 2, there are only 2 outcomes. Which we define as success or failure. And success meaning the thing that we're looking for to actually happen, the outcome that we actually care about counting. And to put some notation on that, we use little p to represent the probability of success. We use little q, which is of course equal 1 minus p, because there are only 2 outcomes, so that's going to happen literally with the complement, is the probability of failure. And 3, each outcome is independent. Now, sometimes that will be painfully obvious when they're independent, but otherwise the problem is going to be stated for you. Then, once you know you've read a word problem and you have this situation, these 3 things are fulfilled for that word problem, what is going to happen is, if x equals the number of successes, then the probability that x equals some particular value between 0 and n, right? You can have 0 successes, or all of them could be successes, or any number in between. That is given by the formula nck p to the k q to the n minus k. So these guys are called the binomial probabilities. And yeah, so these 3 situations have to be fulfilled. So when you're reading something, you should notice when something like this is occurring, and then you know that, oh, I'll be able to use a binomial probability to figure this out, in which case that formula will take effect for a particular k. These guys are called binomial coefficients. Because again, bi means 2. You have 2 outcomes. And by the way, binomial theorem says, I can't help myself. Binomial theorem tells you how to expand a sum of 2 terms, or binomial, to the power n. It turns out that they kind of, each term actually behaves like a binomial probability. it turns out that you would have n choose 0, a to the n, b to the 0, plus n choose 1, a to the n minus 1, b to the 1, plus n choose 2, a to the n minus 2, b to the 2, plus dot, all the way up to n choose n, a to the 0, b to the n. And you can actually realize that that would work. A plus b all squared. We all should know what that is. That's a squared plus 2ab plus b squared. How would I know? It turns out it's actually 2 choose 0 times a squared b to the 0 plus 2 choose 1 times a to the 1 b to the 1 plus 2 choose 2 times a to the 0 b to the 2. Start with a with the highest power, count down, and start with b at the lowest power, count up. And then these guys will give you the coefficients. You will notice that 2 choose 0 is actually 1. B is actually going to, b to the 0 is actually 1, so you're just left with an a squared, plus 2 choose 1 is actually 2. And then you have ab. And 2 choose 2 is actually 1. You have b squared. You get that formula. And you can actually do this for any level, right? So if you do a plus b all cubed, it's going to be 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, and then you do this with the powers, and that's actually how you expand the cube. Yeah?
Are we going to be using this, or did you just show it to us?
Yeah, I'm just showing it to you. I don't think you'll ever actually need to know. But yeah, this coefficients, that kind of thing actually tells you how to expand something. So that's kind of where the name comes from. Now, going back to the example. Example 7. Probability set 2, problem 7. Now, here's the thing, we have a basketball player. Probability, he makes a free throw. Is 70%, which by the way implies the probability he misses a free throw. Is 0.3%. We know he attempts 10 shots. And we're assuming they're all independently, because that was mentioned in the problem. And then we wanted to figure out specifically what is the probability he makes all 10 shots. Makes all 10. B, what is the probability he makes 2, exactly 2. C, what is the probability makes somewhere between 3 to 5, and what is the probability he will make at least 1. Now, you would read this problem, and here's what you would think. Okay, we have this guy taking 10 shots. In other words, here's a guy doing the same thing 10 times over. It's the same experiment happening 10 times, right? That tells you that this 10 in the problem can be thought of as your n. The same thing is happening over and over and over again. He's running the same experiment, taking a free throw. We also know there are only 2 possibilities when this is happening. Either he's going to make the free throw, or he's not going to make the free throw. This here is going to be our success. And this here is going to be our failure. More specifically, this is the probability of failure. It's the probability of success. I want you to appreciate that a success means what we actually care about, what we're counting. Notice that I phrased the question in how many he makes, right? So him making the shot is a success. If the problem was phrased in how many he misses, right? Let's say what is the chance that he'll miss 5? Then this now becomes your success, right? Our success would be his downfall. But that's the thing. Whatever we're looking for, that thing is our success. Find the probability of that, that's the probability of success. So we're looking for how much he makes, we're counting this situation. Okay? Then we have independence. So ultimately you have the 3 situations being fulfilled. The same thing is happening over and over, namely 10 times. There are only 2 possibilities, he makes it or he misses, and they all happen independently. The 3 situations of the binomial probability are fulfilled, which means I can think of this as a binomial probability. And that's important that you know when to do that, because if I give you a problem like this, I'm not going to tell you use binomial probability. I'm just going to give you a word problem, and you have to read it and figure out, oh, it's a binomial probability. So that fulfills all the 3 things that I need for a binomial probability. So once I know that, oh, it's binomial, now I know exactly how to actually solve these problems. So this means, because I know it's binomial, this automatically means I know the values of some of these variables now. N equals 10, my P equals 0.7, my Q equals 0.3, and if X equals the number of shots he makes, part A is actually asking me, what is the probability that X equals 10? So once I know it's a binomial probability, I know the values of all these variables, which I can figure out by reading. Once I know that, I also know what formula would apply here. So this is going to be 10 choose k, p to the k, q to the n minus k. Where here, k is the number of successes I want. So it means the probability of that occurring is going to be 10 choose 10, 0.7 to the 10, 0.3 to the 10 minus 10. 10 choose 10 is actually 1. 0.3 to the 0 is actually 1. Notice that this is equal to 0.7 to the 10. At this point, I want you to appreciate that that actually falls exactly in line with what we know to be independence, right? If all are independence, then the probability of him making the shot is just the product of all the probabilities 10 times. So this is basically, we know this means he's making the shot with a probability of 0.7 10 times in a row. You multiply 0.7 10 times in a row, you get 0.7 to the 10. So that's actually the probability. It actually works out as we would expect. What is this?
Roughly.
0.7 to the 10.
2.8%.
Huh?
2.8.
2.8%?
Yeah.
So this guy who makes 70% of the shots that he takes, the probability that if he takes 10 in a row, he's going to make all 10, 2.8%. So if you guys have some favorite basketball player, and you know his stats are around, he makes like 70% of all the free throws he makes, and someone says, hey, bet you that the next 10 free throws this guy takes, he's going to make all of them. Want to take the bet? We would say no. I would bet against that, because there's only a 2.8% chance that I would be correct. Questions about this setup process? Okay. What's the probability that he will make 2? because we know that the probability of x equals k is nck p through k q through n minus k. So B is asking for what?
Is it 10 choose 2?
Oh, what is it asking?
Oh, p of x equals 2.
So that's going to be
10 choose 2 times 0.7 to the 2 times q to the 8.
right 8 10 minus 2.
How come for this why do you need the 10 choose 2?
Oh, because what we explained last time, remember there were 10 positions?
Yeah.
And I wanted to know how many ways could I choose 2 of those positions to be the made shot and the other 8 to be misses,
Okay.
right? So how many ways can I choose for there to be 2 checks? Well, out of 10 positions, just choose 2 at random. That's 10 choose 2. And I don't care what order they're made in, I just care that he makes 2. So that's where the 10 choose 2 comes from, because this kind of situation can happen in many ways. You could make 2s at any position and miss 8 at any other position. So there are a total of 10 choose 2 ways that a situation like this could occur. And for each one of those situations, there's a 0.7 squared probability times 0.3 to the 8th probability that that situation happens. So we add up all the probabilities because they're mutually exclusive, so there's 10 choose 2 of these expressions that we need to add. And ultimately, so 10 choose 2, that's going to be 10 times 9 over 2 times 1, that's 45. So that's going to be 45 times 0.7 squared times 0.3 to the 8th. Or you can just type this into your calculator if you don't know that. What is that? Come in?
0.014%.
0.014%?
Yeah.
It's not very likely. So, if someone were to ask you for a bet, you want to bet that he'll make 2? No, I'd rather bet that he makes 10.
It's 0.14%.
0.14? It's still more likely that he makes all 10 than he makes 2. Which makes sense. I mean, if he averages 7 shots, making 10 is closer to making 7 than making 2 is. So that actually makes sense. 0.14% that he's going to make 2 and miss 8. What about C? What would C look like? Yeah?
So C, you do like 10 choose 3 times 0.7 to the 3 times 0.3 to the 7 plus the same thing for 10 choose 4 and then plus 10 choose 5.
So that we can write it as he will make somewhere between 3 and 5. Which, because of we have mutual exclusive here, this just means the probability of x equals 3 or x equals 4 or x equals 5. This is, because we're mutually exclusive, the sum of the probabilities. Probability of x equals 3 plus the probability of x equals 4 plus the probability of x equals 5. Right? He can make exactly 3 or exactly 4 or exactly 5. He can't make all of these at the same time. So we add the probabilities. And yeah, for each of these, we will do that formula. 10C3, 0.7 to the 3, 0.3 to the 7th, plus 10C4, 0.7 to the 4, 0.3 to the 6th, plus 10C5, 0.7 to the 5, 0.3 to the 5. Type that in. If you're putting that in your calculator, I'll probably put parentheses around each of these just to make sure that there's no conflict calculators actually has the ability to do multiple of these. It'll be a different command for each calculator, but at the very least, I want you to at least write this down so I know that you were thinking of it, and then you can use the function in the calculator. Chances are an approved calculator, a non-graphing calculator, won't be able to do it, but it might. You can look it up if your calculator can do it. What is this? Probably he makes somewhere between 3 and 5. He'll make 3, or he'll make 4, or he'll make 5. He'll make one of these. Yeah.
I got 14%.
14%? Roughly? Do you agree? Do you have anyone else getting 14%?
Yeah.
You got 14%? See, there's a 14% chance that he's going to make between 3 and 5. What about the last one? Probably he makes at least 1. What would that look like?
That's just 1 minus 9. So you can.
Yeah, but write down what are you looking for? At least 1. What does that mean?
Greater than or equal to.
Greater than or equal to 1, so, right? That's one of those key phrases that you should remember. At least means greater than or equal to. At most means less than or equal to. So what is the probability that the number of shots he makes is greater than or equal to 1? Well, technically, this is going to be P of 1 plus P of 2 plus P of 3 plus P of 10. Or just realize that this is 1 minus the complement, probably that it's less than 1. Which is 1 minus, well, there's only one way to be less than 1. He has to actually make 0. So you can use the complement. Or by the complement probability. I can just do the opposite, which in this situation is a lot nicer. I only have to do 1 calculation instead of 10 of them. And this is going to be 1 minus 10C0 P to the 0 Q to the 10 minus 0. 10 choose 0 is 1. There's only one way to choose nothing from 10 things. So pretty much you have 1 minus 0.3 to the 10. And again, that one is pretty intuitive because making 0 means he misses all 10, which means you have 10 multiplications of 0.3, probably a 0.3 every time they're independent. You'll multiply them together. But we're saying that does not happen, so it's 1 minus that. And what is that? That's actually going to be really high up there.
0.0, I get 0.9999.
0.9999. What?
4.
It's just like 99 point. 99994. So that I put money on. If this guy has a track record of making 70%, meaning out of 10 shots we expect him to make around 7, I'm pretty sure he's going to get at least 1. It'll be a cold day in hell before this guy actually misses all 10. Not going to happen. Not that it's not possible. There's a very small chance that it's possible. That is an example of a binomial probability. Questions in general about this concept, idea, calculations, anything. Okay, so just remember, binomial probability, you read a word column, look for 3 situations. You're repeating the same thing over and over. Only 2 outcomes, success or failure, and they're all independent. Once you have those situations, we're looking at a binomial probability, which means you should be able to pick the total number of times the repetition is happening, the probability of success and failure, and if you're looking for a certain number of successes, that will be the probability. And then based on the situation, you should know what specific probability you're looking for. That will allow you to know how to apply that formula. So yeah, that is binomial. Here's another important idea I want to introduce here. Now, there are a bunch of situations, binomial probability included, where we realize when we're in those situations, how the probabilities work out, it's pretty much guaranteed by some formula. There's a strategy for doing it, and I can actually write this down in a formula. This leads to the idea of probability distributions. There are some times, in certain situations, probabilities are predictable. Not that the outcome is predictable, but how you would calculate the chances of each outcome is going to be predictable. Whenever we have such a situation, we like to use something called a probability distribution to describe the situation. So, definition. The probability distribution. Technically speaking, it is a function, but for us, we can think of it as a table. Which lists all possible outcomes. And the probability of each outcome. Probability of each outcome. i.e., let X represent a possible outcome. Then a probability distribution looks like the following. You are going to construct a table. Where you're going to have X and all possible outcomes. That's A, B, C, and it keeps going until some final possibility here. And in the second row, you're going to put the probability that X is one of these guys. So here you're going to list under A the probability that X is actually A. Under B you're going to list the probability that X is actually B. Under C you're going to list the probability that X is actually C. And so on and so forth. What is the probability that X actually outputs star? Now, a lot of times A, B, C, these will be numbers, but they could also potentially be qualitative, right? For example, I could do X is the outputs of me flipping a coin, in which case I would put H and T, and then a half and a half, right? So these guys may be qualitative. Qualitative means they're not described by numbers, they're described by some quality, or quantitative means I can describe these by numbers. Here's an example. Examples. Probability distribution for a coin flip. We write that as a table. What are the possible outcomes? Well, heads or tails. What is the probability of the outcome? Well, this is going to be 1/2, this is going to be 1/2. This is the probability distribution for a coin flip. It is simply a table with two effective columns. I list all the outputs along the top, and I list the probability of each output underneath that output. I can also talk about the probability distribution of rolling a die. Well, the possible outcomes are I can roll the dice and I can get 1 or 2 or 3 or 4 or 5 or 6. And the probability of each of those, chances of me rolling a die and getting a 1 is a 6. Chance of me rolling a die and getting a 2 is a 6, is a 6, is a 6, is a 6, is a 6. I could do, for example, probability distribution of rolling 2 dice. What are the possible outcomes and finding the sum? What are the possible outcomes in this situation? It's an experiment we've done before.
2 through 12.
Right, 2 through 12. Right, so when I'm rolling a die, the outcome can be 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. So this would be a table with 12 columns or 11 columns, whatever. What was the probability of getting a 2? You guys remember? There was one way to get a 2. You had to roll 2 ones. That was 1 out of 36. Then getting a 3, there were 2 out of 36 ways. One was a 2, the other is a 1, and vice versa. To get a 4, there were 3 out of 36 ways. To get a 5, there were 4 out of 36 ways. To get a 6, there were 5 out of 36 ways. To get a 7, there were 6 out of 36 ways. You might remember that one was the peak, and then it started to descend. So this is 5 out of 36 ways, 4 out of 36 ways, 3 out of 36 ways, 2 out of 36 ways, and there was only 1 out of 36 ways to actually get 12. That's the probability distribution of rolling a die and finding the sum, right? So that all it is just me listing all the possible outputs and the probability of each output. Putting that in a table, we say I've constructed a probability distribution. So there is something called a binomial probability distribution. We call this the binomial distribution. And so this is x. So now the binomial distribution, probably that x equals k, is going to have n things in it. So x can be the success never happens, or it happens once, or it happens twice, or it happens k times, all the way up to happening n times. What is the probability of it happening 0 times? Well, it's n choose 0, p to the 0, q to the n. P to the k. Yes, p to the 0, q to the n, because n minus k. What is the probability of it happening 1 time? N choose 1, p to the 1, q to the n minus 1. Happening 2 times, n choose 2, p to the 2, q to the n minus 2. Dot, dot, dot. Happening k times, well, n c k, p to the k, q to the n minus k. Dot, dot, dot. N choose n, p to the n, q to the 0. So for any random binomial probability, this table can tell me about the probability distribution. And this is nice because it allows us to calculate binomial probabilities very quickly. So what your calculator will have, for example, is there's a table like this programmed into your calculator. So sometimes your calculator will have a function binomial, and you will tell it what is n, what is p, what is q, and your calculator actually computes this table, and then once you ask it, what is the probability that 5 successes? It's just going to look up in the table for the 5th position, and it's going to output that number on your screen. Right? So it allows you to do a quick lookup of probabilities once you do a probability distribution. Somebody can ask you a probability, okay, for that chance, that's the probability. So they're really useful for many reasons. Here is I remembered I wanted to say something, but now I forgot what I wanted to say. Probably not important. Here's one other reason that a probability distribution is important. It's important for many reasons, but here's one of them. There's something called expected value. This is simply if an experiment is performed many times, the expected value of the experiment is the average. You can sense the mean. Expected value of an outcome is the average value of the outcomes. So, for example, in the basketball example we did earlier, I can say the expected number of successful shots was 7. On average, this guy makes 70% of the shots he's making, so out of 10 attempts, I would expect him to make 7. If I wanted to bet how much this guy is going to make out of 10 shots, my bet would be 7. That one would be the expected value. So this is called an expected value. So now you might say, well, what if he was taking 300 shots or 172 or some other random thing? How can we calculate the expected number of shots that he would take? How to calculate expected value? Way. There are many ways, and depending on the distribution, is to use the probability distribution. Specifically in this way. But suppose I have some probability distribution. And we have a finite number of things. This is finite math, we're doing finite probability. So one possibility for the output is x1, another is x2, another is x3, another is x4, dot, dot, dot. Let's say it goes all the way to n possibilities, right? Finite probability. So these can be numbers or letters. Could be heads or tails, could be green, blue, red, could be whatever. This guy here is going to be the probability that you get x1. This guy here will be the probability that you get x2. This guy here will be the probability that you get x3. Probability that you get x4, dot, dot, dot. Probability that you get xn. And this means, so here I'm going to introduce the notation. The expected value of x. X is what I'm calling any possible output. So this is the notation. So this is expected value of x. Is going to be equal to the following sum. I'm going to take the output, multiply it by the probability. Do that for every one, and then I'm going to add them all together. This is going to be x1 times probability of x1 plus x2 times the probability of x2 plus xn times the probability of xn. This is going to give us the average value. This will be the value that I expect. This will be the value that I'm going to make my bet on. This controls more of your life than you realize. When you go to buy car insurance, for example, they take a lot of stats on you. What's your age? Where do you live? What's your zip code? What's your credit score? What's this? What's that? Basically what they're doing is they're comparing you to some database that they have on a bunch of statistics. And so they're pretty much trying to fit you in a table somewhere. There's going to be a table of, oh, let's say there's an event where this guy's going to cost me $5,000 in the first year. What is the probability of that based on the expenses? Probably there's an output. Okay, he's going to cost me $10,000 in the first year. What is the probability of that? He's going to cost me $15,000 in the first year. What is the probability of that? They'll have this table, this huge database. And pretty much what's going to happen is once you put in all your data, it looks up in the database and it creates a probability distribution for you. And then they say, what is the expected value of how much money this person is going to cost me in the first year? So let's say they come up to $12,000. This person is going to cost me $12,000 in the first year by doing this calculation. Now you know what they do? His insurance premium is going to be at least $1,000 a month. That's how you get the price. They put you in the database, they calculate the chances of you having certain accidents, costing them a certain amount of money, compute the expected amount of money you're going to cost them, and then they charge you the insurance premium to make sure we're making at least that. So when you go, when you sign up for your car insurance and it says, okay, yours is $100 a month. That means they expect you to be in some sort of accident that's going to cost them $1,200 over the course of a year for you specifically. Whereas your friend in a different situation, oh man, that dude, 17 years old, he's trying to insure a red Ferrari. This kid is just, no. He's gonna probably cost like $12,000 in the first year. This kid's insurance, $1,000 a month. Whereas you have a little beat up Toyota Corolla, it's not gonna drive very fast. You know, you're like 42 years old. This guy's not gonna cost me that much money. How much did I expect him to cost? This much. Divide that by 12. That's his insurance premium. Well, they decide first what profit they want to make. Okay, what would our shareholders expect from us? So get that plus a little cushion so that we can cover operating costs, all that good stuff. And that's how they get you. And a lot of things, a lot of the prices that you pay for things comes from them finding an expected value. And that is pretty much we will end there. Right on time. Let me turn this on.